most of the questions to after the seminar part of it, and then we'll have a period of time for open questions from the audience. And then around 5 o'clock, we'll probably have the audience leave, and then the committee will stay here and have a few more questions for her for a little while, and we'll proceed from there. So I'll let you go ahead and get started. She'll be talking about the work she's done on boron doping to build power diodes out of diamond. Go ahead.
Great. Yeah, thank you, Dr. Grocha. Can you guys hear me okay? Because this is good.
Perfect.
Okay. My name is Shannon Nicely, and I'll be presenting for you guys today my PhD defense work on the boron doping of single crystal diamond for high power applications. So I'll start with an outline. I'm going to go through the motivation for this work, including diamond as an electronic material and a little bit about Schottky barrier diodes, the application that we're going to be looking at. Then I'll go through some experimental techniques, including chemical vapor deposition and the FTIR technique that we use to determine the boron concentration. And then I will run through the results that we have on lightly boron doped, heavily boron doped, and on so diamond is an excellent electronic material because it has a number of really outstanding properties that make it good for electronic materials. So what you can see here is that if we look at band gap, and band gap, you want to have a high band gap in order to operate at high power. You want to have a high mobility in order to operate at high frequency. And then thermal conductivity helps with the device performance as well, which is the size of these circles. And you can see that diamond is really the only high band gap, high mobility semiconductor. It has the highest thermal conductivity of any material. So it would think about diamond. Typically, you think about the kind of diamonds that we use in jewelry, which are very pretty, but are actually insulators. To turn the diamond into an electronic material, we make it into a semiconductor. And we do that by adding boron. Boron has one fewer electron. Actually, I'm going to point at this one. And I'll point at this one. One fewer electron than carbon, which means that it creates a space into which an electron can move, which is called a hole, because it's essentially an electron hole, which gives it conductivity. It also gives the diamond a blue color. It's what gives the Hope diamond its So if we want to use, let's see, if we wanted to use an electronic material, what would we potentially use it for? So one of the applications is the Schottky barrier diode. So a Schottky contact is an ohmic contact on a piece of semiconducting material create a diode. And what that essentially means is that it allows current flow in one direction. So the ideal diode would have in the off state the infinite capacity to hold back resistance without providing current, and in the on state, the infinite capacity to pass current without any voltage. So no matter what voltage you put across in the forward direction, it would conduct in the, and if you, whatever voltage you put it across in the negative direction, it would be off. So current flows in one direction. Now in an actual diode, you don't get this ideal characteristic. Instead, you have some non-idealities. There's a slope to the forward resistance, to the forward curve, which is the resistance material, which causes heat dissipation and is not advantageous to that. There's a voltage that you have to reach before it starts conducting current in the forward direction. There is leakage current. A small amount of current gets through the diode even at low voltages, and as you go out, high voltage diodes, we need a very high breakdown voltage, and that's part of what we'll be looking at. So some of the kinds of structures that you can make diodes out of on diamond. So we grow diamond, I'll talk about this in a minute, on an insulating substrate. So if you wanted to make an ohmic contact and a Schottky contact on the same piece of material, you have to put them on the same surface. So this is called a planar structure for that reason. If you wanted to, the problem here is that you have to conduct through this lightly doped diamond, which has less conductivity than heavily doped diamond. And also the ohmic contact isn't particularly good to lightly doped diamond. So you can overcome those problems a using a heavily doped diamond layer. So we make the ohmic contact and the Schottky contact to get into this active region, the lightly doped diamond, and we get better conduction, although we still have some issues here. Because there's the current is flowing in this curved U-shaped fashion, we have a nonlinear current density, which causes a concentration of the current at the contact edges, which causes a lower breakdown voltage. In addition, because typically it has to travel quite a long ways, we get a higher on-state resistance because of the horizontal component. So you can overcome these problems by going to a vertical structure. So in this case, we have uniform current densities because we're now conducting from top to bottom, so all the lines go in the same direction. And we have, for a well-designed vertical architecture diode, a shorter path between the Schottky contact and the ohmic contact, which reduces the on resistance. So this will lead us to the things that are a problem with boron doped diamond growth in general. We need this lightly doped layer. We need to achieve this thick, heavily doped layer. And in addition to this, there's also a problem with dislocations that I'm going to talk about much later in the talk when I talk about developing a new architecture for a Schottky barrier diode. So what we're going to look at in this dissertation, the objectives of this work, are going to be to achieve a lightly boron doped diamond layer, a regime for high quality deposition that also has boron concentrations in the range of about 10 to the 16 to 10 to the 17. And I'm going to talk about what that means in a second. And to identify a regime that minimizes the defects. For heavy boron doping, I'm going to look for concentrations above 10 to the 20. And I'm going to talk again about what that means in a second. And to identify a regime for high quality growth. And then I'm going to present a design for a Schottky barrier diode that optimizes, that improves the device characteristics by minimizing those dislocations I'm going to talk about a little bit later in the talk. So these are the three main objectives that I'm going to be talking about today. So how do we grow diamonds? Well, we grow it by microwave plasma assisted chemical vapor deposition. So essentially what we do is we have an energy source, which is microwave power, and we contain it within a brass resonant chamber. We have a probe that excites in this chamber a TM013 mode, which has 3 electric field maxima. We take the bottom of those nodes, we enclose it inside a quartz dome, we pump all of the air out to vacuum, and then we flow in through the gas inlet only the gases that we want present in the chamber during growth. So that's hydrogen to reduce the nucleation of, or to eliminate the nucleation of graphitic phases, and methane, which acts as our carbon source, and in our case, because we're boron doping, we also include a boron source, which is diborane. So the actual process looks, schematically sort of like this. So we have energy that comes in, it creates a plasma, and then we have gases that come in that get split into more reactive species that then add a little bit at a time onto the diamond surface. So in this case, the blue is supposed to be sort of like boron, and the yellow is supposed to be sort of like carbon as it gets added, essentially one atom at a time. So how many atoms of boron do we actually have going into our diamond? So before I talk about this, I thought it might be smart to put up something for people who aren't terribly scientific about the kinds of units and numbers that I'm going to be talking about. So carbon organizes itself in this tetrahedrally bonded lattice, and it has in this square lattice cell, a lattice constant, they call it, of about 3.5 angstroms. An angstrom is 1/10 of a nanometer, and a nanometer is 1/1000th of a micron, and a micron is 1/1000th of a millimeter, and that is 1/1000th of a meter. So this is a very, very small unit, which means that as you make a box of this that's about a centimeter on each side, you come up with 10 to the 23 carbon atoms in that box. So if I say, for example, that there is 10 to the 22 atoms per cubic centimeter of boron, that's about 5% of the material is boron, which is an awful, awful lot in a semiconductor. Whereas if I'm at a range of about 10 to the 17, that's roughly 1 boron atom for every 2 million carbon atoms. So just to give some perspective before I start talking about how I want to achieve certain doping regimes, right? So how do I actually find what that boron concentration is? So what you're looking at now is an FTIR transmission spectrum. So picture, for example, how stained glass works. You have a lot of panes of multicolored glass, and the impurities that are in that glass make them appear a different color by absorbing wavelengths of light out of the white spectrum. The same thing happens in diamond. There are impurities in diamond, for example, boron, that absorb certain wavelengths out of the electromagnetic spectrum. And as we look in the IR spectrum, so this is infrared, this is like where microwaves and radio waves and all that are. As we look with wavelengths, so this is going to give wave number in per centimeters. There are 2 regions here that are important for our discussion today. One of them is the 1 phonon region, and that means that you need to have a singular lattice vibration with every absorption of a photon in this region, which means that you have to have a defect that breaks the lattice symmetry in order to make that possible. And so nitrogen, for example, in these very lightly doped samples, causes the majority of this absorption, but also boron can cause that kind of absorption. And out here past what they call the Raman energy, there are electronic transitions. This means that a photon of light can have the same energy as an electronic transition in the diamond lattice to the boron acceptor. Okay, so for lightly doped samples, we're going to be talking about one of these electronic transitions, and that's the area under the absorption peak at 2800 that I just showed. So if you have something that is related to the acceptor, what you need is a calibration for obtaining the amount of boron and a way of measuring it. So we measure it with the FTIR, and we use the calibration that was developed by Collins and Williams. And the absorption coefficient is related by the natural log of the ratio of the doped spectrum to a baseline spectrum divided by the sample thickness. So essentially what we do is we take this spectrum and we put a baseline across it, and we measure the area under here. And all the absorption that takes place under that area is related to the boron acceptor. So we take a baseline, we turn that into the absorption coefficient, and we multiply it by this 8 times 10 to the 17. So this works well for lightly doped samples, that's samples with very low boron concentrations. But as we increase, so I'm showing you here the ratio of boron to carbon in the plasma feed gas within the CVD reaction. As we increase that, we see that, that this works great. You can draw a baseline no problem for these lightly doped samples. However, as you get higher and higher boron concentration, you start to see that it's very difficult to draw a baseline here due to this broadening, and then eventually at the highest limit, you're above detection limits due to photoionization in the sample. So for very heavily doped samples, we need to look to a different part of the spectrum in order to figure out how much boron is actually in the sample. So then we turn to the 1 phonon spectrum. So for samples that are lightly doped, this is dominated by the nitrogen absorption in the underlying seed. But above concentrations of approximately 10 to the 18, we start to see that that boron is a dominant effect, and you can use this calibration to determine the amount of boron in your heavily doped samples. So we use the calibration that was put forward by Davies and confirmed by Gearhart, and I'll talk a little bit more about that in a second. Which means that we take the absorption at this peak and we multiply it by 2.13 times 10. Is what is called SIMS, secondary ion mass spectroscopy. This is a totally different way of determining the amount of boron. You take a beam of ions and you essentially bombard the diamond sample, and then you see what comes off with a mass spectrometer detector. So that gives you exactly what's in your sample as a function of depth. So as you mill away more and more of it, you can see how much boron there is, and you can see how much nitrogen there is, or whatever else you're looking for. So let's see. Also, so using that SIMS technique in a SIMS process that was verified for diamond, and comparing that same Davies equation that I showed earlier that we're going to be using, Jamar Richard and his coworkers recently were able to show very good alignment between the numbers, and so we have pretty good confidence that the numbers that we're seeing are related to the actual amount of boron in the sample. Okay, so let's see. Let's talk for a second. So we want to look at lightly boron-doped films first. So let's see if it's possible to get this electronic grade lightly boron-doped diamond that we can make our Schottky barrier diodes with. So recall that we're going to be using this microwave plasma-assisted chemical vapor deposition machine, and we're going to be growing on high pressure, high temperature seeds. To get diamond, you need to start with diamond, otherwise you get polycrystallinity, and we want single crystal diamond. So we use single crystal diamond substrates. We acid clean them and hydrogen etch them before deposition, and we deposit them with hydrogen methane and originally just diborane with substrate temperatures between 900 and 1,000 degrees Celsius. So in initial experiments that I did sort of at the very boron to carbon in the gas phase. And even with these small amounts of boron to carbon, we saw really quite a lot of boron ending up in the sample. And this is because of what is known as the reactor memory effect, which causes unintentional doping. So this reactor has been used for very heavily doped samples, and that boron gets into the walls. And then as you run the growth process,